this, our main idea here is going to be about an idea called integration. And that's how this is kind of going to start. But before we do that, because integration is going to involve accumulating, adding things up, I want to take today to talk about a bit of notation that you're going to see in this. And hopefully those of you who have taken stats, I showed you a little bit of this during stats because some of the formulas involved this notation. This is called sigma notation. This is a more capitalized sigma than like your standard deviation symbol. This sigma means sum. It means add. And it is a shorthand way of writing out a long string of addition, of adding things up. And so a couple of bits of terminology. This I equals 1 is called the index. It is making note of, and usually we put it in the subscript of the A. And this part of the sum is a way of saying how many terms we are adding. And so usually this n is some number. And so I equals 1 to n means that we are going, or I equals 1 to 10, for example, means that we are going to add up 10 different numbers. And so that's what this is being used to notate. And so then we'll put up a sub 1, a sub 2, plus a sub 3, and then the last term will be a sub n, the nth term. And so let's look at a couple of examples here. Properties. Some of these properties are very, very fancy ways, not in the notes, just watch. These are very, very fancy ways of writing simple ideas that you already know. For example, the sum from 1 to n of k times a sub I, k times that term, is the same as if I bring the constant out in front and then take the sum. So another way that that can be written is that this sum on the left would be k times a sub 1 plus k times a sub 2 plus k times a sub 3 all the way across. That would be the sum is equal to, here comes the right side, is the same as taking k times this entire sum. All the way up to a sub n. So this idea right here is something you should already be familiar with. What do we call this? Distributive property. This is just a distributive property written out in a really fancy way. Or if you want to think about it the other way, this is the same as describing how to factor out a greatest common factor. Right. This one, and you can write it out to convince yourself, this is a fancy way of talking about the commutative property. Saying that we can add in any order. other summation formulas. The sum from 1 to n of c, some constant, is c times n. This is defining multiplication. This is saying that, for example, if I have the sum from 1 to 6 of 4, right now there's no variable attached to it. This is just saying to add up 4 6 times. 1, 2, 3, 4, 5, 6. Which is the same as 6 times 4. So this is, again, just a fancy way of defining something that you already know. I'm using these examples to kind of get you comfortable with what some of these summations are saying to do. So the sum from 1 to 6 of 4 is defining what 6 times 4 is, saying to add up 4 6 times. Multiplication is a shorthand way of writing addition. Now here's where we get to the more interesting formulas. The sum from I equals 1 to n of I. So let's say we have the sum, let's use a number for n. Let's say 100 of I. So I is the index we're using to say that we have 100 different terms. And what is the term? Well, the term is the number that we're adding is whatever term we're on. So we start with 1, and then our next number that we're adding is 2 because it's the second term. Next number we're adding is 3 because it's the third term. All the way up to 100. And what this is saying is that there is a formula for this that you can prove, and that you can work with shorthand in getting. Is that this is the same as n times n plus 1 over 2. What is n? N is the number up here. It's 100. And so the shorthand way to get this answer, instead of having to add up all these terms, is to take n, 100, times n plus 1, 100 plus 1, and then divided by 2. And that's the sum of the first 100 numbers. And then some fancier, and then when you get to a higher level math class, you'll actually prove these formulas. But for now, these are just interesting formulas for you. There's also a formula for some of the first I squared terms. So if you want to know what 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to 10 squared is, it would be 10 times 10 plus 1 times 2 times 10 plus 1 all over 6. And that'd be the formula for the sum of the first n squared terms. Here's the formula for the sum of the first cubed terms. So if you wanted to know the formula for the first 50 cubes added together, 1 cubed plus 2 cubed plus 3 cubed all the way up to 50 cubed, that's a formula that has been proven to give the sum of those first n cubes. Now, these are not formulas that you'll have to memorize. If any of you have been interested in or have talked to anyone about doing scholastic bowl or math team, this might be a useful formula to know, because sometimes those come up on things like math team or scholastic bowl. But otherwise, this is not a formula by any means that you'll need to memorize or anything like that. But you should be able to take this and write it as this. That's what I want to make sure that you get out of today, and making sure that you can write. So for example, let's take some sums. And we'll just do the first three here. That's what we'll focus on today. So the sum from I equals 1 to 6 of I. Well, that means we're going to accumulate from 1 all the way up to 6. That's what we're going to be doing. So our first term is 1. Our second term is 2. Our third term is 3. Our fourth term is 4. Our fifth term is 5. Our sixth term is 6. Add all these up. This, by the way, another fun math fact. This, by the way, is called a pyramid number because you can use these to make a pyramid. 2, 3, 4, 5, and so on. And then it would tell you how many dots are in the pyramid, the sum of these numbers. 3 and 3 is 6, and 4 is 10, and 5 is 15, and 6 is 21. And that would be your answer to that sum. Or you could use the formula. Since we're adding up the first 6 numbers, this should equal 6 times 6 plus 1 all over 2. That's 6 times 7 is 42 over 2 is 21. That would be the formula. But this is how the addition looks. That's what I want to kind of hammer in today. So I want you to take 2 minutes and see if you can think about what these next two are going to be. Notice that neither of them start at 1 this time. And so the first number you're plugging in for I and j is not 1. So for that third one, there should be 5 terms that you're adding together. you don't get the exact calculation of the third one, that's fine. I'm more interested in you being able to write out the sum, the kind of long form sum. What number goes here? 0, because this starts at 0. We're starting at 0 and going up to 5. So our next one is 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, which hopefully you recognize that 0 plus 1 is 1, and 1 plus 1 is 2, and 2 plus 1 is 3, 4, 5, 6. Oh, it's the same sum we just did. It's still 21. So this is just a different way of writing the exact same sum. The next one first number we write is what? 3 squared. So your 9 is coming from squaring 3. So we're starting with 3, and we're going up to 7. So 4 squared, 5 squared, 6 squared, 7 squared. That is that sum. So those are some of the simpler formulas. You can see that they're going to get more complicated, and we'll talk about more of that tomorrow. Now, I want to introduce the main idea that we're going to talk about tomorrow so that you can see what it looks like. And why we're talking about these additions and sums. We've covered limits and their use in finding slope of a tangent line. We talked about this concept of a limit to find derivatives. Now we're going to work backwards. If the derivative tells us slope of a function, what would going backwards tell us? In other words, you already know that f of x is x squared. Hopefully you already know that f prime of x is 2x. And that this gives me a function of what the slope of the tangent line is at every x value. And so f prime of 3 is 6, means that the slope of my tangent line at 3 is going to be 6. Well, the derivative of x squared is 2x. Now we're going to start to ask questions like, and again, I talked about this with some of you who are at some of the review sessions. We'll practice more of this later on this week. We're looking at what function, when I take the derivative of it, will give me x squared. So now you're going to work backwards. And what we're going to talk about today is what this function is going to tell us. This is going to be called an antiderivative because it's working the opposite direction of the derivative. And what this function is going to tell us is going to be area, or in other words, accumulating an amount. So that's what the antiderivative is going to tell us. And we're going to talk about something pretty similar to what we talked about before. Is what we can do is our goal is going to be to find this area between the curve and the x-axis. And we're trying to determine what this area is. So that's what the antiderivative is going to tell us. Now, here's a question I want to leave you with here. We looked at a curve, and using the slope of a secant line like this, we picked a point very close to it and used it as an approximation of what the tangent line looked like. And the way that we got to the tangent line was we let this point get closer and closer and closer to the original point until it was hypothetically on top of it. And that's where our limit came in, is that we took the limit when this distance between the points approached 0. That was the idea of the derivative. So we're going to think about what thing. We don't know how to find area formulas for curves, but we do know about area formulas for things involving straight lines. So what can we use to approximate this area? How can we make a good guess at what this area is going to be? And how is that going to turn into a limit in the same way that the derivative is going to? So that will be the idea that we're going to talk about